Okay, so we're going to start the next talk, which is about quantum computing, and it's being presented by Barry Bird, who is a professor of mathematics and computer science at Drew University. So without further ado, Barry, take it away, and you can share your screen wherever you want.
So I don't need to share my screen because I can show you my slides over here. And if you can't read them, let me know, yell out, and I can make them bigger. One of the things you should do, well, a little bit of ado before we begin. First of all, I like to talk to a real group, real people. So if you feel inclined, or if it's okay with you, feel free to please turn on your video so that I can see you, and that'll give me the feeling that I'm talking to other than a computer screen that I'm doing right now. And interrupt with questions by yelling out anytime. I like questions, and I'm not very good at keeping my eye on the chat. So anytime that you have a question about anything that I say, just unmute your audio or just keep it unmuted and yell out your question. That's kind of the way I like to work. If you ask a question and I don't know the answer, that'll be okay. I'll just make something up. Another thing that you should know is I'm not going to be doing using the share screen aspect of Zoom. So what you want to do is either click on my tile and select pin, or alternatively in the upper right-hand corner of your Zoom window, there's a little box that's, I think it's labeled view. And what you want to choose there is not gallery view, where you see everybody in a big tiling thing, but speaker view, where you see me in a larger screen. So once again, if I'm too small for you, and if you can't read what's on my slides here, go to the upper right-hand corner of your Zoom window, click on view, and choose speaker view. And that'll help you see what I'm doing. And in case anything on the slides is too small, let me know. I have all kinds of mysterious ways of making them larger. I've been teaching now online at Drew University for almost exactly a year. And so I've got a lot of tricks up my sleeve. Okay, so once again, turn on the video if you can, turn on your audio if it doesn't become too much of an interference thing, and let's begin. As a way of background, I've given talks on quantum computing before, but I usually, when I talk about quantum computing, I talk about some mysterious quantum algorithm. And what I'm trying to do today, for the first time, is just talk in general about quantum computing, because I find that people want to know, just, get an overview of what's going on and what's the whole thing. So I'll start with a picture. That's what a typical quantum computer looks like these days. Actually, the processing unit itself is this thing down here. And can you see that? That's my little dot there. My little red dot is traveling. Yeah. And it's that thing at the bottom there. Mm-hmm. That's the QPU, the quantum processing unit. That's the quantum computer. The rest of this stuff is just controls of one sort or another. It looks very nice because it's got all sorts of gold-looking parts to it. If you are in the presence of a quantum computer that's operating, you won't see all this, because all this is dipped into a cylindrical vat, and that cylindrical vat is super duper cooled to less than 1 degree Kelvin. And the reason for the cooling is to slow everything down so that we have a fighting chance of managing the quantum phenomena that are supposed to go on inside the QPU. Then that cylindrical box, that cylindrical tower that this thing is dipped in, is going to be attached to a standard classical computer. A classical computer is like the one that you have in front of you, or like the phone that you use, or like the, well, any processor that you use nowadays. that doesn't make use of quantum computing phenomena. So you never use a quantum computer in and of itself alone. You're going to have one of these things, and it's going to be attached to a classical computer. Part of the processing will be done by the classical computer. Then at certain times, it'll send signals to the quantum computer to sort of take over, do the quantum computing magic, and send its answer back to the classical computer. All right. Who's doing quantum computing? All these folks. And some of them are there because they're big names that you recognize: Google, IBM, Microsoft, Amazon, Intel. One of them, D-Wave, I made sure to put there because it's the most prominent name right now in the manufacture of real, honest-to-God quantum computer equipment. D-Wave is maybe the most well-known name for having quantum computers that are actually available. And there are other quantum computers, of course, that are available, but D-Waves are kind of the most well-known. There are many other players in this arena. The most well-known, I guess, are Beidou, Rigetti, Strangeworks, dozens and dozens of others. Some of them are making pieces of quantum computers. Others are just doing research and using others' quantum computers. Now, in the top realm there, IBM and Microsoft, and maybe even one or two of the others, you can actually program yourself on their computers. So IBM has a website called the Quantum Computer Experience, and Microsoft has quantum computing for Azure. And Microsoft was just made public a few months ago, publicly available a few months ago. IBM has been publicly available for a while. You can actually go on their website, write yourself some quantum computing programs, and use their equipment. In addition to using their equipment, which you're going to use sparsely, they're not going to let you use it all the time and hog the equipment. But in addition, you can use simulators. So if you want to goof around with quantum computing, for example, you can go on IBM's website. There's a lot of learning materials there. You can learn how to use, you know what? I'm in the way.
Are these homegrown computers, or are they actually people that manufacture?
Well, give me a sec here. First of all, I'm in the way, and I forgot to get myself out of the way here. And now, was I in the way for my beautiful picture of other things? I'm gonna backtrack. Here we go. And now a phone that I never use is ringing. Thank you. All right, so this is me, Barry Bird, quantum computing, Drew University, barry@bird.org. And here's my beautiful picture of a quantum computer. Oops. And there's my little red pointer. And it's going toward the bottom of the screen. And there's the QPU at the very bottom. Okay, and now and now I really will get out of the way. Is a list of companies most prominent in my mind that are doing quantum computing right now. And somebody had a question and I ignored it because I was busy moving myself. What was the question?
Are these companies have homegrown quantum computers, or are the actual companies that make are making these computers quantum?
They're companies that make the quantum computers, and so D-Wave makes quantum computers. And as far as I know, Rigetti and Beidou do also, but I'm not absolutely sure about that. But then companies like IBM, it's a combination of making quantum computers and buying equipment from other people. The significant thing about companies like IBM and Microsoft at this point and on this slide are they make access to their computers available publicly. So you can go on the IBM computing website and actually create a quantum computing program of your own and run it either on their simulators, which means it runs on classical hardware that's just trying to look like a quantum computer, or you can actually get some time on their real live quantum computers. And there's lots of educational material on the IBM site so that you can learn what to do and how to construct a quantum computing program. Most quantum computing programs are sort of Python based right now. Microsoft is based on a language called Q#, which is very much like its C#. Colin, you asked the question, did I answer it?
Yes, thank you.
Okay, all right. So
Accurately, are they able to simulate the quantum computer on the classical computer?
say that again?
How accurately are they able to simulate quantum computing on the classical computer?
I think the accuracy is not the pain point. The pain point is the speed. So they can quite accurately simulate what the quantum computer will do with one possible little glitch that I can talk about if you want. The difficulty is that a quantum computer can solve problems unbelievably faster than a classical computer. So if a classical computer is trying to behave like a quantum computer, it's going to run much slower. So the kinds of problems that you can simulate on a classical computer are going to be much, 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 much smaller toy problems than the ones that you can actually solve when you've got a real quantum computer in the mix. Now, everything that I just said requires a little bit of grain of salt like talk. So let me do 2 grains of salt here while I just move something to another screen of mine. First, accuracy. The quantum world uses real, honest to God, 100% randomness. And that's very hard to simulate in the classical world. So if you have a classical computer that's trying to simulate a quantum computer, then unless they do something really exotic, the kind of randomness that it's going to create will be what's called pseudo-randomness. It looks random, but it's not really random. It looks random and it has all the characteristics of a sequence of random numbers, but behind the scenes, it's reproducible randomness. And that's going to be a difference between real quantum computing and the simulation of quantum computing for some simulators. So that's accuracy. On the speed side, quantum computing is much, much, much faster. Real quantum computing is much, much, much faster. Except that these days, the amount of quantum computing that they can do, the amount of quantum computer power that they can have is extremely small. So the notion today that you can, in real life, get a lot more out of a quantum computer than what you can get out of a classical computer and a classical computer simulation is, I lost track of the beginning of my sentence. Right now, quantum computers can't do that much because we're still in the engineering stages of creating larger and larger quantum computers. I think the question person was Mike. Did I answer it?
Yes, thank you.
Okay, all right. So let's march on here. And I just need to see what, oh yeah. Let's talk about quantum supremacy. So Google had a project called Sycamore, has a project called Sycamore, that in October 2019, they announced solved a problem in 200 seconds that would take a classical computer 10,000 years to solve. And some number of months later, a group in China showed that a classical computer could solve it in 5 days. Well, big deal. The point is that the quantum computer is going to run much, 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 much faster on this problem. And the notion of quantum supremacy is the notion that we can solve with a quantum computer problems that cannot, for all practical purposes, be solved with classical computers. And this example, this is pretty much one of the very, very few examples we have of real honest-to-God quantum supremacy. This example serves as a sort of a prototype to show us that it's possible. Now, there are other problems that we know of that if we have hefty enough quantum computers, we could solve in seconds that would take not 10,000 years, but billions of years for a classical computer to solve. So we're trying to work engineering-wise toward more and more better and better quantum supremacy to the point where quantum computers can solve what are really, really, for all practical purposes, impossible for classical computers to solve. And the reason right now that we don't have any really, really good examples of quantum supremacy that work is, if I go back a couple slides, there we are. This QPU that's down at the bottom, here's my red dot going down and getting to the bottom of this thing. That QPU, this is a picture of some quantum computer or other. I'm going to take a guess that that quantum processing unit QPU has no more than about 50 qubits, which is like having a 50-bit computer, classical computer. And that ain't much. That's not enough. We need somewhere between 1,000 and 10,000 qubits in order to maintain, in order to get anything like quantum supremacy that I'm talking about here. So right now, engineering-wise, we're in the 50 qubit era. We are not in the 10,000 qubit era that we'd like to be, but advances are being made very, 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 very quickly. Okay. What I want to do now, any questions on what I've talked about so far? Okay. Let's march on. By the way, I just saw a little note that I've never seen before that said the speaker highlighted your video. I don't know what that means. What speaker? What did it, the speaker?
It just means that everyone can see your screen on a large screen instead of like a little small cube.
Oh, okay. All right. Very good. Excellent. Okay, here we go. Once again, let me know if there's something that you can't see. I just want to talk about what's going on behind the scenes in quantum computing. So what's a bit? A bit is either a 0 or a 1. Wow, that's pretty simple. It's a really useful concept, but it's not a lot of information. If I have 1 bit, then all I know is yes or no, true or false, the cat is alive or the cat is dead. You know, the socks stink or the socks don't stink, yes or no, 1 or 0. And that's not a lot of information stored into a single bit. Now, what about a qubit? Well, for reasons that I have gotten into trouble trying to describe, a single qubit is a continuum of possibilities. To start with, you have to take two numbers to describe it. You can't describe a qubit with just one number, 0 or 1. And that 0 or 1 is going to be in a continuous range anywhere between, well, if we look at this 0 here, and we look at this 1 here, then instead of 0, we could end up with 1/2, we could end up with 1/3, we could end up with 1 over the square root of 2, we could end up with something that's very, very, very close to a 1. But we need that other number too. We can't do with just the 0 here or the 1 there. And the reason we need two numbers to describe a qubit is because these numbers don't have to be numbers between real 0 and real 1. For example, they can be 1 over square root of 2, 1 over square root of 2, but they could also be 1 over square root of 2 minus 1 over square root of 2. As long as the squares of these two numbers add up to 1, we have ourselves a qubit. So a qubit is like a bit, except it's got much more possible states that it can have. And in fact, the number of possibilities branches out beyond real numbers. If you're familiar with imaginary numbers, complex numbers, I can have a qubit that's in a state that looks like this. Its top number is 0, and its bottom number is, I don't know, imaginary square root of 1, or minus the square root of 1, or anything like that. As long as this number, when I square it, plus this number when I square it, adds up to 1, then I've got myself a qubit. So if I can control one qubit, then I have a hell of a lot of information in that qubit to work with. And in fact, if you want to know what's really going on behind the hood, under the hood, the top number is the probability of seeing 0 when you measure the qubit. Well, it's actually the square root of that probability. And the bottom number is the square root of the probability of seeing 1 when you measure it. So let's say, for example, that I have a qubit that's in this state. If I square the top number, I get 1/2. If I square the bottom number, I get 1/2. And that means that when I observe this qubit, I'm going to have 1/2 of probability, 50% chance of seeing 0, and 50% chance of seeing 1. Now over here, if I square these two numbers, I'm going to get 3/4 and 1/4. So here, the probability of seeing 0 when I actually measure this qubit, when I examine it, is going to be 3/4, 75%. And the probability of seeing a 1 will be 1/4. And probabilities are, interestingly, the only thing we can talk about when we talk about measuring qubits.
What is the significance of some of the numbers being either negative or imaginary?
So that's phase. And that's simply another characteristic of the qubit beyond the probability characteristic. And so it's like you've got a wave, you know, there's particles and waves, that's particle wave duality. And the amplitude of the wave is the probability, but the amount that the wave is either in phase or out of phase with the other part is that difference between, say, plus 1 over the square root of 2 and minus 1 over the square root of 2. In the case of 1 over the square root of 2 versus minus 1 over the square root of 2, you've got two waves whose humps and troughs are 180 degrees out of phase. And these out of phases have to be described by complex numbers. And the reason they have to be described by complex numbers is because you have to be dealing in 3 dimensions. And so you can't just talk about waves that are in and out of phase in 1 dimension. You have to go in and out of phase this way and in and out of phase that way. That's a very, very quick explanation. Whoever asked that question, did I sort of answer it?
Yes.
Okay, all right. Now, and my phone's ringing. Alexa, hang up.
Incoming call.
All right, and it'll ring in another yeah, that's CBS calling to remind me for the 90th time that we have medicine to pick up. Okay, here we go. Yes. Quiet. Okay, now, I've been asked in many talks how are qubits implemented, and so I decided to actually answer that question. You can think of a qubit as a spinning electron. Is it spinning in a counterclockwise direction or a clockwise direction? And if you do what they call the right-hand rule, then one of them is called a half spin up, and the other is called a half spin down. And a half spin up would maybe represent a 0, and a half spin down would maybe represent a 1. Now you can put a qubit in a state where it's neither definitely spinning up or definitely spinning down, in which case we say that it's in a superposition of the 2 possibilities. And a superposition of the 2 possibilities, for example, could mean that it's got a 75% chance of spinning upward and a 25% chance of spinning downward. And when I phrase this in terms of probabilities, I'm talking about nature. I'm not talking about, hey, it's spinning one way or another, but we don't know which way it's spinning. I'm talking about nature not knowing which way it's spinning. And I'll get into that in a minute. It's an important kind of idea. Instead of which direction an electron is spinning in, you can also talk about a polarized laser beam. So it can either be polarized in the vertical direction or the horizontal direction. And if you've done any viewing of, well, in the old days they used to use these for 3D movies, but I guess, yeah, they do now. They do now. The wave of 3D movies has passed, but once we get back to movies, kids' movies will still be available in 3D, and those glasses use polarized light. And polarized light beams, again, the complete vertical polarization can be considered 0, the horizontal polarization can be considered 1, and values in between represent the superposition of states. In practice, IBM and Google have a superconducting circuit loop. So the circuit is the current is oscillating on a superconducting circuit, and they zap it with microwaves to make changes to the state of the qubit. A group called IonQ uses electron levels in an ion. So if the electron is at its base state, that might represent a 0. If an electron is at its first state beyond the base state, that may represent 1. And what's in between those two states may represent superposition, the simultaneous possibility of the electron being on both levels. And when you zap these things with a laser, that puts these things in either superposed states or does what you want them to do when you manipulate them. Now, one interesting possibility is braided paths of electrons. And I'm going to fake it on this one. I don't know too much about what's going on there, but the idea is that you send electrons through braided paths of some kind of material. And what you end up having is a multi-particle assembly that behaves in one way or another like a particle, a single particle. And in fact, physicists actually call it a virtual particle. It is a particle of some sort. And I studied topology when I was in school, and I have no idea. I've asked several people, what's the connection between these braided paths of electrons in topology, and no one's given me an answer. So there's something going on there. But Microsoft is big on experimenting with that. And the problem is that there isn't yet a real proof of concept that that would work. But if it does work, that would be exciting, because we know that if it does work, these braided paths of electrons will be much more stable and easier to control than the current oscillating in a superconducting circuit loop, or than the electron level in an ion. And if we can have topological quantum computing working, we can implement many, many, many more qubits with greater reliability than we can with the other technologies. Okay, so far? All right, let's see. I bravely and foolishly labeled these slides quantum mechanics explained in 6 slides. And now you know that I'm full of baloney. Let's say that we start see my red dot there? There it is. Let's say that we start with a qubit that represents 0. Now we're going to hit it with a laser or microwave or whatever it is that we do. And what we're going to do is hit it with something called the Hadamard operator. And what the Hadamard operator does is it puts it in a superposition of states. So after hitting it with the Hadamard operator, this thing is going to be, the resulting thing is going to be in a superposition where nature doesn't know whether it's spinning up or spinning down. And when I say that nature doesn't know, what I mean is that when we measure it, we're definitely going to see a 0 or a 1, but we don't know which we're going to see. And there's no way that nature knows what we're going to see. Now, at this point, you may say, come on, nature knows what's going to happen. We just don't have a way of figuring that out. And that was an argument that Einstein was having with Bohr for many decades. And Einstein lost and Bohr won. And the proof that Bohr won was done in the 60s, I believe, by an Irish physicist named John Bell, who devised an experiment to show that there was no hidden variables here. So that when a qubit is in this superposed state, there's nothing in nature that remembers whether measuring this thing is going to give you a 0 or a 1. And that's one of the really bizarre features of the way qubits work. But it's a feature that we can exploit. If you've heard about Schrodinger's cat, I would never take my cat to the Schrodinger Veterinary Service. It's the same sort of idea. We just don't know. Nature doesn't know whether the cat is alive or dead. So there's no way of telling whether a particular cat qubit is going to end up in a 0 or 1 state when we open the box. And then, so Schrodinger says, hey, what about the cat? Does the cat know? And that gets us traveling down a philosophical rat hole, but that's okay. I said there would be 6 slides here. So let's talk about another phenomenon called entanglement. Nature knows that if you do this 1,000 times, then you're going to get close to 500 zeros and 500 ones. If you've applied the Hadamard operator, and if you've applied other operators, then nature might dictate 3/4 of the time you'll get 0 and 1/4 of the time you'll get 1. So that means that probability is built into nature and the way qubits work. First hint then is that when we do quantum computing, we never run one program, get a result, and then stop. We run the same experiment 1,000 times, 10,000 times, 50,000 times, take a look at the aggregated results and see what probabilities we end up with. That's always the way quantum computing programs work. Now, entanglement. Let's say we start in a little lab, and the lab is going to be in New Jersey, and we have 2 qubits, and we somehow zap them with something called the Hadamard operator and something else called a C-0 gate. And we get them in a state that's called entangled. Entangled is maybe one of the more bizarre things in nature. After doing that, I'm going to send one of them to the moon. Now, bear with me, because as I send it to the moon, in today's reality, there is no way that I'm going to be able to keep those 2 qubits in an entangled state. I just can't do it. I don't have the technology to reliably make it so that they're still entangled by the time one of them goes from the Earth to the moon. But in theory, this can happen. So what I can have in theory is a qubit on Earth that's entangled with a qubit on the moon. And I've somehow set it up so that the result that I get when I measure one is correlated with the result that I get when I measure the other. Let's say I decide that first I'm going to measure the one on Earth. Again, not even nature knows what the result will be. If I applied just the Hadamard operator to begin with, nature knows that half the time I'll get zeros and half the time I'll get ones. That's all that nature knows. And there are no hidden variables. There's no secret sauce in here where nature can know that ahead. When you make a measurement, when you make a measurement, nature just says, I don't know what you got before this, but half the time you'll get 0 and half the time you'll get 1, and it'll occur in absolutely random order, the zeros versus the ones. Nature doesn't know what the result will be, but if the result of the measurement on Earth is 0, then because of entanglement, we know for dead certainty, then the result here will be 1. Now, if you think about that, that is philosophically absolutely bizarre. And the reason it's so bizarre is because nature doesn't know whether this is a 0 or 1, But once you measure it and it's been determined, nature suddenly knows that this is either a 0 or a 1. The two particles, the two qubits, are correlated somehow, but neither of them knows which it is, whether it's a 0 or 1, until one of them is measured. And that entanglement is what's used to bring about magic results in computing that quantum computers do. I'm going to pause for a minute, and the next thing that I have to talk about is much less theoretical. So I want to stop here and see if there are any responses, questions, anything like that. No? Okay, here we go. Let's get back to Earth here. Applications. Just a quick survey. I don't know, thumbs up or in the chat or something like that. How many of you are familiar with actual coding on a regular computer, a classical computer, in any shape or form, in any language?
Sure.
Yep, okay. All right, who's not?
I'm not.
Okay. Okay, all right. An unrepresentative sample, but that's okay. I'm just, you know. Oh, good, great.
You got 1 bit up and 1 bit down.
Well, the other thing is, when you become familiar with classical computing, then any problem that a person throws at you, you can kind of slowly but surely work out a solution. Am I right about that? I'm gonna glance at everybody, and let's say somebody says, hey, write 1 million lines of code to do such and such and such and such. And at first you may feel intimidated, but after a while you'll say, well, I'm going to break this down into pieces. And I know that if I do this, I'm going to have to do that. That's an if statement. And I know that I'm going to have to repeat this several times. That's a loop. And by the time you're done, if you've taken it slowly enough, you can kind of visualize, if not all the details of the solution, the outline of the solution. And if you're familiar with programming, you know what I'm talking about. Let's see, somebody in the chat says logical thinking will get you there. Absolutely. And if you're not familiar with programming, just take our word for it that in the classical world, any well-specified problem, there's at least a brute force way that you can think of solving. I'm not talking about artificial intelligence, crazy things, but I'm talking about just, add the numbers from 1 to 1 million, or do today's payroll, or something like that. If there's a recipe for solving it, you can find it. But that is not the case with quantum computing, at least not yet. So, for example, there are specific algorithms that we have in quantum computing to solve specific kinds of problems, but we don't yet have a way of generalizing that to be able to solve problems of any sort. My favorite 2 quantum computing algorithms are Grover's search algorithm and Shor's algorithm. Grover's search algorithm says that if I have 4 things and one of them is taller than the other, I can find which one is than the others. I can find which one is taller by looking at one thing, not all 4 things. If I have 100 things and one of them is heavier than the other, then I can find out which one is heavier than the others by examining 10 things, not having to examine 50 things or 100 things. So Grover's search algorithm makes use of entanglement and makes use of this, crazy continuum feature of qubits to reduce the amount of time that it takes to find something in an unordered list. Shor's algorithm, you may have already heard of that. Shor's algorithm is a way of cracking codes. And what Shor's algorithm does is that it makes use of the cyclical nature of prime factorization to pretty quickly get at the factorization of extremely large numbers. And if you can factor extremely large numbers efficiently, then you can decrypt many of the things that are being sent by conventional encryption methods today. So if a malicious person gets hold of a quantum computer that can perform Shor's algorithm efficiently, then they'll be able to get my credit card number, and with any luck, they'll be able to pay my credit card bill. Okay, here we go. Simulation. Yeah, if you're trying to solve a problem in chemistry, then a lot of the times quantum phenomena are involved there. And so what the simulation people do is they take just the quantum mechanical part of the problem and they simulate it with qubits on a quantum computer to see what results they get. And they can then extrapolate that to the real life application. And that's kind of fun. As is the truth with everything in quantum computing, that's in its infancy. Now, quantum key distribution is interesting because it's actually being used. And there are companies that sell quantum key distribution hardware and software. And the idea there is as follows. Once you make a measurement on a qubit, you can't tell whether it started off in the 0 state or the 1 state. There's just no way of knowing that. So if I take a qubit and I apply Hadamard to it, and it's in a half and half state, if I am an interloper, an eavesdropper, and I try to measure what's being transmitted, I really can't tell for sure what it started out as. Nature can't tell. Nature doesn't know what it started out as. So imagine that Alice sends 100 qubits to Bob. And in the middle, Eve, the eavesdropper, tries to read those qubits. Well, what's going to happen is Eve's going to mess them up. Eve's going to make it so that the transmission gets garbled. And with a rather clever scheme of comparison, Bob and Alice, the sender and the receiver, can sort of compare notes and tell whether there was an eavesdropper in the middle. Because the eavesdropper really honestly destroys the information in the middle if the eavesdropper tries to read it. And so Bob and Alice can tell now if the transmission was good or the transmission wasn't good. And if the transmission was good, they can use it as the encryption decryption key for further transmissions. And this is actually being used in practice, mostly government applications right now, but it's becoming more widespread. Called quantum key distribution, and it's maybe the at this moment, the most fruitfully implemented part of the quantum computing world. One other application that's really big on the horizon is quantum machine learning. Yeah, machine learning is hot stuff. Alexa, tell me a joke. Oh, come on. All right, she's not going to tell me a joke. It's machine learning that gets her to understand my voice.
Barry, I just want to offer a 5-minute warning.
Absolutely, absolutely. I got one more slide. Oh, you want to offer 5-minute Q&A?
So we have 10 minutes between talks. So I figure 5 minutes for Q&A and another 5 minutes for people to, if they want to transition to another track.
Right. But so I understand that my talk officially ends at 12:15. Am I right?
That's correct. That's
all right.
Correct.
So let me finish up here. Machine learning. If you ask me a question about it, I'll have to make up an answer. I don't know how it works, but it's apparently extremely promising in the quantum world. The combination of machine learning and quantum computing. Just one more slide. What are the big problems? As I said earlier, the algorithms are relatively scarce. When we stumble on an algorithm, the world celebrates, but we don't have a lot of them yet. It's just not the case that in the quantum world, you can hear a problem and use your logical thinking to compose a solution, for sure. The other big hurdle is that the hardware is noisy. So right now we're at the scale of what's called noisy intermediate scale quantum, which means we can do quantum. It's extremely error prone, and we don't have enough qubits yet to work with. As a matter of fact, when I'm talking about 1 qubit, the actual quantum computer is actually juggling about 10,000 of them and aggregating the result. And do I have another slide? I do. That's my hello, goodbye slide. And now it's time for Q&A. We've got 3 minutes.
Just a comment. When you called Alexa, my Alexa went off because it's right
here. Of course.
Here.
Do you know the story? Do you know the story about the dollhouse? I'll tell it in 2 seconds. A child said, "Hey, Amazon, buy me a doll." I don't want to even say the word. "Hey, Amazon, buy me a dollhouse." And then a couple of days later, a dollhouse showed up at the family's doorway. So this was announced then on the TV, on a TV newscast. And after that, dollhouses showed up on the doorsteps of a lot of people who were watching the newscast.
That's funny.
Can we quickly see the other 4 slides that explain quantum mechanics?
I showed 6 of them.
No, you only showed 2.
Oh, let me just back my way up here. Whoops. All right, now I'm under pressure. And now I have to move myself out of the way. So here's one of them. Here's the next one. There's the next one with the Earth, right? That's 3. That's 4. That's 5. I'll get out of the way here. And that's 6. And yes, is it extremely crazy of me to say that quantum mechanics is explained in these slides? Of course. But those are my 6 slides.
I just wanted to mention that D-Wave does have a way of programming their computer, their quantum computer through the cloud, and they give you like a minute of time for free.
It's cool. Yeah. I want to get into the Azure realm, but I just haven't had time to try it out. I've tried IBM, and that's fun. And there are all kinds of nice simulators. There's something called Quark that is really, really fun to play with. It's not for real, but it's great fun for illustrating and for learning. And hey, that's it for today, right?
One last question. Is
Sure.
there a good introductory book on quantum computing that's not super math heavy?
It depends on what you call super math heavy. There's one called Programming Quantum Computers, and I actually used it in a course, and it's got some of the math but not all the math. And if you send an email to barry@bird.org, then I can send you a link.
Thanks very much.
Thank you.
I have a question, Barry. Do you feel you have enough material to, let's say, put together an advanced undergraduate, senior level or even junior level college course as a technical elective on quantum computing?
Well, I've done it. It was what we have at Drew University now is a course that's offered jointly by the physics department and my department. So a physicist does a quarter of the course, and then I do the next 3 quarters. And whether you'd call it advanced or not, I don't know. It's advanced enough for us to call it, we call it an intermediate course. And it covers, I think it covers a lot of the basics really well.
Do you include sort of hands-on activities, actual, is it all theory or are there hands-on sort of project or activities?
So we had, the first time we offered it, we did not do much hands-on, but hands-on is probably going to be part of the next run of it, because we can start using things like the IBM quantum experience and Microsoft's Q# language. So we can start doing a lot more of that in the next run of the course. The first run didn't even have the physicist, so I just had to lie about physics during that run, and it was mainly, we were just gearing up theoretically, but we're going to add a lot more real stuff as we go along. It's part in an introductory course to get very deep into the hands-on part of it, but we're going to do our best.
Great, thank you.
Okay. All right, and I have to hang out here and stay here, right? Because I'm on next in this thing.
Yes, we'll just going to wait for the actual time, because if someone is coming from another track, I would like them to be able to start and see the introduction of your next talk.
Okay.
So we'll start that at 12:25, and in case someone wants to take a break, or if you want to take a break, have a glass of water or something, that's a good time. We'll start at 12:25 the next talk.
So what I'll do is I'll set up for the next talk.
Sounds good. Thank you so much.
It'll be a completely different
question. Is there a good website to access what's going on within this field? Where they're tracking the news and also maybe help learn how to use these languages for quantum computing?
So the two that I would recommend most are the IBM Q quantum experience and Microsoft's Learn Quantum, I think it's called. But generally, when I have a question about quantum computing, I just go to my address bar and type in the question and see what comes up. There are, I don't know, like anything else on the web, there are thousands and thousands of resources right now. And the ones that are best for you are the ones that you find.
Fair enough.
Okay. And now I have to get myself set up.
Can you hear me? Hello, can you hear me?
Yeah, we can hear you.
Okay, so two quick questions. I mean, I want to see Professor Bird, whether have you tried those environment, IBM and Microsoft, and how much you like it or not? I couldn't. You are muted. You're muted. Okay.
Can you hear me now? Yeah?
Yeah. Yes.
Okay. Yeah, I'm of two minds on that. I like IBM because there are so many resources there. It's an incredible number of resources. And on the IBM site, you can actually use real quantum hardware. I like Microsoft because the language that they use isn't Python based, and I'm not a Python fan. Instead, it's C# based. And that's close enough to my native language, which is Java, to make me feel comfortable doing the programming. So do I have a preference for the two? I don't know. Yeah.